Good afternoon, everyone. It's my great honor to share my recent research result to you. Today, my topic is continuum mechanics of extreme response analysis and measurement noise reduction for Stokes flow, considering uncertainty. So this is my content introduction, and show the basic method for finite element method. Extreme response analysis is about the analytical continuum mechanics and the measurement noise reduction. And finally, I will share my closing remarks. So as we know, there are many uncertainties when we do the experimental the measurement. So especially for mechanical engineering, want to measure deformation. So here I show the measurement map. So the horizontal axis is the strength view. It's about the window size, and the vertical axis is about the measurement resolution. Here the measurement is all about strength. So strength basically is the relative comparison about your reference length, right? So we need the latest grating. So this is the classical the way to think about how to develop some new measurement method. So classically, when we want to enhance the measurement accuracy, you need very fine the grating, so-called we can call the interferometry. And recently, I do a lot of microfluidics experiments. So we know we do have many uncertainties. So here I come up with an idea how to quantify, how to analytically to catch the uncertainty from the source to the response. So this is the cell, the picking up experiment. When we put some like trypsin, like a protein to make a new curve for the cells. Now the cell may have some polarity. So when we turn on the electrode, and we can collect the cells we want. But somehow we may lose some the very good cell. So we need accurately describe the experimental uncertainty, or we can call the error. So I will skip any details. So usually when we write an article, we need to describe what the standard deviation about your experimental result. So I know I may get quite several questions. What's the error source? What's the deviation? Why do we have this deviation? So like this, control, measurement, and after the cell removal, if our experimental system is robust, actually this after the removal should be identical to the original control experimental setting. But usually we cannot get identical one. So I'll skip many details. So I think 2 points. One is identical those extreme events. Second point is how to remove those noise. So here I pick up the easiest fluid dynamics model called Stokes flow, because this flow is linear model. It's very similar to the solid mechanics, the linear elasticity. So I adopt the wind engineering the method for predicting extreme response called load response correlation. As long as we can describe the external loading, the uncertainty, in terms of mean, standard deviation, and the pair correlation coefficient, we can analytically get the solid system extreme responses. So similarly, if we can have some linear system, here I show you the Stokes flow, because Stokes flow is linear system, so I can adopt the whole thing, the whole framework to do the extreme response prediction. Second point is, here is my former advisor. He used called experimental field projection to remove the experimental measurement error, or you can call measurement noise. Same idea, because this is the linear system. So in microfluidics, we can write down, we can describe our system in terms of the linear, you can call elasticity matrix and the response and the excitation. So I use finite element the model to describe the system we have. So as I mentioned, if we put the average plus or minus, here is the peak vector, because usually the experimental data, we have the Gaussian distribution. So if we control 1, 2, 3, even 3.5 times the standard deviation, we can reach even the 99.96%. We can cover the whole data set. That means we can reach the extreme events. So I will skip the details, because they are all analytically. So it's very convenient for computational guys to get these numbers, because D is the stiffness matrix. So I have some result. So here is the lead-driven cavity flow. It's a very typical demonstration example. Suppose the excitation has some uncertainty. They have some uncertainty. We describe the uncertainty in terms of average, standard deviation, and the correlation coefficient. As long as we have this clue, we can analytically get the extreme response prediction. Here, many dots mean I think 10,000 sampling tests. So I think this result is quite reliable. So I just skip those results. I will move the second point, the measurement noise reduction. Okay. So because we know the signal contains the data plus noise. So our job is to make the noise manage as much as possible. So here the theory is about we just compare the measurement and the theoretical distribution, and try to minimize their discrepancy. I think constraint is important. We believe loss data distribution should follow linear elasticity. So I think this is typical procedures. You can list the quadrature and use the Lagrange multiplier. So I think here finite element framework is important, because you can express your data points through the nodal variables. So here I think, as you can see, the third column is the measured data. And after the noise removal, we can get the clean the measurement field. So I show. And also we apply this technique to real experimental the data set. Here is the fly brain, and because a fly brain, if the fly has some disease, the brain may have significant deformation. I mean the brain. So, but biologists they just took image, but they cannot extract numbers, right? But like mechanician, you can get a number from the image through this we call reference map technique. Basically, we describe the mechanics theory in Euler framework instead of Lagrangian, because if we describe the solid the material constituted law or equivalent equation in Euler framework, there's no gap between the surrounding fluid and the solid materials. I'm still working on this topic. Hope I can share my result with you soon. I think I might talk. I think it's up to here. Thank you very much.